What's going on, everybody? This is Mr. Diamond, slightly sleep deprived, and you know that is the best possible time for me to be doing some physics example problems. So we're going to be doing our friction problems. I'm also going to be doing one that does not involve friction, just because I realized I forgot to actually record a video for that. I know, shock, I forget something. I apologize for that. So we're gonna first work out this normal problem right here. I'm gonna do a quick friction problem and then another friction problem involving this same box from up here. So for most of the things this chapter, we want to go ahead and be drawing a picture. So in this one, we've got a 10 kilogram box on a frictionless horizontal surface. So I've got my box. It's 10 kilograms. Now in the position that this box is sitting, it's going to have gravity acting on it. Force of gravity. And because it's not moving at all horizontally or vertically, there must be no net force, and that means there must also be a normal force acting upon it. There's no motion to the sides. In this case, the sum of all the forces must be 0 because it is not moving. If it was moving, there would be some kind of force in action with it. Or it would be at a constant accelerate or a constant velocity, but it's sitting still. There's no force, net force acting upon it. So that must mean that my normal force must equal force of gravity. They must be canceling each other out because they must have the exact same forces in this first case here, because well, there's nothing else acting upon it. So, and this is for example A. So for example A, we know that the force of gravity is equal to mass times gravity. In this case, our mass is 10 kilograms. And gravity is negative 9.8. So we've got negative 98. Which again, negative is not telling you that it's a less than 0 number. It's just telling you it's directed downwards. So it's negative 98 newtons. And that also must mean that, so when I say that they are equal, I guess I shouldn't be saying that they are equal. I should say that the force, normal force plus the force of gravity is equal to 0. They're going to be the same magnitude, but they're not going to be angled the same direction. So what number must the normal force be to counteract this? Well, normal force is equal to the force of gravity, just oriented in the upward direction. To cancel this out and make it equal 0, it must be 98 newtons. Okay, well, what if we've got our same small box, but now in the sum of the forces in the y direction is going to be equal to, we've got force of gravity plus force of the normal plus force from the push. And if it's being pushed down, we still know that it's going to be in place. It's not going to actually be moving. So all of these forces added together must still equal 0. It doesn't say that it's mentioning anything about burrowing into the floor or being pressed into the dirt or anything like that. It's still stationary. So all of these things must add up together to equal 0. Now we know because the force of gravity is pulling down at 98 newtons, you need at least 98 newtons to do any sort of like lifting. We don't have any information of how much you'd have to push into the ground. We're going to just assume that it's going to take way more than we're ever going to reasonably actually get in this problem, or it's not actually a factor in this problem. We know the force of gravity. The force of gravity must be the same thing, and we know the force of the push. So we know force of gravity is still going to be negative 98. We don't know the normal force, but we know that the force of the push is downwards, and it's 40 newtons. So it's going to be plus a negative 40 newtons. Now, you could do minus 40. I like to do the plus a negative 40 newtons because I like to make sure that I indicate that all of these forces needed to be added together. This first one and this one just were negative forces. So if I simplify this down, I'll get 0 equals negative 138 plus the normal force. And that should tell you, well, I need the normal force to cancel out. The weight is going to be the same. The weight is not going to be changing based on this, so that stayed the same. But our normal force is now bigger. Our normal force is now 138 newtons. Our normal force must be 138 newtons because it has to account for the extra force that you're pushing down with it on. And when you're pushing down, the harder you push down, the table like underneath me right now is still supporting my hands as I push down on it. And so when I push, it's just pushing up with more normal force to support it unless I can overcome the actual things keeping this table in place and then break the table. But we're not working with any examples like that. So just really quick, I'm going to do this up here. So force of gravity in this case is negative 98, and force of gravity in this case is also negative 98. And you can probably make that guess, and you would be correct. Force of gravity in this case is also negative 98, not 9.8. The first example, our normal force was also 98. And our second one, our normal force had to be 138. It had to raise because by pushing down on something, you're making it take more work or more force to keep it in place, to keep it supported. So for our last one, we kind of got the same situation. Some of our forces, the only forces they'll be acting on this box, if this is our base situation here, is we've got normal force and gravity. Now we're also going to be adding force of the pull upwards. And it's not moving. It's not enough newtons of force to lift to be able to lift it up because this thing weighs 98 newtons and you're only lifting with 40 newtons. So the sum of the forces is equal to 0. There's no acceleration. So we'll go ahead and do equals. Well, our gravity is still going to be negative 98. We don't know our normal force, but now we have a positive 40 newtons as our value because it's directed in the upwards direction. It's going to be a lift instead of a push down. So if we add and simplify all these together, we'll get 0 equals negative 58 plus normal force. So what number must we cancel out our negative 58 with to make it equal 0? Well, normal force must equal 58. So in our situation here, our 10 kilogram box, while it's at rest, gravity and normal force are equal to exactly the same thing. But you can change that number by pushing down or lifting up on that box. When you push down on it, the surface below it has to increase the normal force and increase the thing pushing back up. This is why when you push down on a scale, you actually will increase it even though the mass has stayed the same. So like if you just laid your hand on a scale, it'll weigh a certain amount. And then when you push down and you apply force to that scale, it will increase the number, even though the mass and the gravity on your hand is still the same, because the push down of you is making that normal force, making the force that the scale is pushing back up on you increase and making that number get bigger. And if you lift yourself, if you were to like hang from monkey bars and just have your feet barely touching a scale, that would be like lifting you up, and it would lower the normal force and it would make it look like your weight was even smaller. So if there is upwards pull on something, the normal force will lessen. And if there's downwards pull on something, the normal force will tend to increase. If you're assuming that gravity is pointing the opposite direction of the normal force, which usually is the case. We'll get to inclines where it's actually a little bit more complicated than that. Okay. It's a little rambly there. As I mentioned, I'm sleep deprived. But we're focusing more today on friction. And if you need more examples of these, let me know. I will happily do some more of those. So I'm going to take my box. I've got a 15 kilogram box. It's on a wooden table. What force do you need to get it moving, and what about to keep it moving? If it has a coefficient of kinetic friction of 0.2, coefficient of static friction of 0.4. So in this situation here, I've got gravity pulling down. The box does not mention it's accelerating, so upwards, so it's got to have a normal force keeping it in place. We're going to assume we're going to push it to the right, so that's going to be F of the push. And then making it difficult to do that is going to be backwards, is going to be F of friction, FFR. So first, some of the forces in the y direction. Let's list them out. We've got normal force, and we've got gravity. And there is no vertical acceleration that it mentions. It does not talk about the box flying away, so the sum of those forces must be 0. And in that case, we know that that means that whatever the force of gravity is, that will also be our normal force. So force of gravity is equal to m times g, which is equal to, in this case, 15 times negative 9.8. So I got negative 147 newtons. So that's directed downwards. And that means that the normal force, because these things must add together to be 0, must be 147 newtons directed upwards. So not negative. Let me draw a dividing line so these numbers don't get too muddled up. Okay. So to get it moving in the x direction, we're going to have a force of the push plus the force of friction. In this case, we are going to have some sort of movement. So we're going to have equals ma. We're going to need to know what is the force you'll need to do to overcome static friction, and we'll eventually want to get it to actually start moving. So that means we'll need to figure out what push would equal the maximum of static friction, and then what push would be needed to cancel out the coefficient of kinetic friction. So first case, we're going to do to get it moving. We need F of friction is equal to the coefficient of static friction times the normal force. Coefficient of static friction is 0.4. Multiply that by the normal force, which is 147. So 58.8 newtons. So in order to get there to be any movement, you would need to get it moving, you will need a force greater than, do it the other way, a force greater than 58.8 newtons. But once you've overcome static friction, because that's the maximum amount of value that the static friction can prevent you from moving it, you won't actually need that much to keep it moving. Once it's moving, if you just want to maintain, you just want to overcome that kinetic friction, you will need to do the same problem. But this time, our force of friction is going to be the kinetic friction times normal force, which is going to be 0.2 times 147. So you get 29.4 newtons. Here. That's what I get for starting my circle and not knowing where I was going. Again, if you can't tell, I'm a little exhausted. So to keep it moving, you're going to need 29.4. Now, I'm going to back up. I'm going to talk through this whole problem because I kind of just started going through the calculation. I want to make sure you understand. So this 15 kilogram box was sitting on a table. And our question is, what force do we need to get it moving, and what about to keep it moving? While the box is on the table, there's gravity pulling down, the normal force supporting it. If we push it, we'll be going one direction, and friction will be impeding us and trying to stop us from continuing to push it in that direction. We know that there is no upwards motion because the problem doesn't mention that. So that means that the sum of the forces in the y direction, the normal force and gravity, must cancel each other out. They must be equal to 0. And because of that, we know that means that the normal force must be equal to the force of gravity, just oriented in opposite directions. So the force of gravity is 147 newtons downwards, and the normal force is 147 newtons upwards. We needed to solve that because friction is based on the normal force. Friction is a ratio of how much of the normal force there is, because that's based on how much the ground is having to push up into it. And we take this number here and we have to plug that into our friction equation. The force of friction is equal to the coefficient, either of static friction or kinetic friction, depending on the situation, times normal force. Static friction can be anywhere up to a maximum force of the static coefficient times the normal force. So 58.8 newtons. If you were to push on this box with 10 newtons of force, it would give you 10 newtons of kinetic or of static friction backwards, and it would prevent it from moving. And if you push with 20 newtons, same situation, 25 newtons, 30 newtons, 40 newtons, 50 newtons, 55 newtons. Not until you hit exactly 58.5 have you matched and you've reached the limit that static friction can push back on you. If you go even 0.1 over or 0.001 over, you just need to go a little tiny bit over that 58.8, you have now overcome static friction and you can push and you can move that thing. And once it's moving, once it's started going, you no longer care about static friction anymore and you switch over to caring about kinetic friction. So in this case, kinetic friction will have a force of 29.4 if the object is moving already. So that means once you get it going, you actually just need an initial push of a little over 58.8 to get it started. And if it's already moving and you're just trying to maintain that speed, whatever speed you've got it to, and you want to keep it not decelerating, you just need to constantly overcome friction. And in this case, the frictional force is 29.4. So you just need to keep applying 29.4 newtons of force over and over and over again into it as you're pushing it. And that will keep it moving at the speed that it was moving at when you started applying that force to it. So sorry if that explanation could have been done better justice during the beginning of the problem, but I also just realized I was very cramped for space, and now we're almost 20 minutes in the video, and I did not want to have to go back and do another one. Okay, we are now on number 3. Now I have enough space to work with on this one. We should be fine. I should be able to kind of talk through in a little bit more detail. So we've got a 10 kilogram box on a table. And I'm going to draw my picture first over here, and then I'll draw the individual ones that I need. Got my 10 kilogram box on a table. My coefficient of static friction is 0.4. My coefficient of kinetic friction is 0.3. Describe what happens when you push with these 3 different amounts of force. So let's go ahead and figure out what we've got. So first, all of these situations are going to have normal force and force of gravity. They're all going to have a force of a push, and they're all going to have a force of friction. And let's look at situation A. In situation A, there is no movement in the y direction. So some of the forces in the y direction must be 0, which means our normal force plus our gravitational force or weight must be 0. That means that they must be equal to each other. And if we know that the force of gravity is equal to our mass times acceleration, or mass times gravity, which is equal to, in this case, we actually did this already up here. You notice it's a 10 kilogram box. We got a negative 98 newtons. And that means our normal force must be canceling that out. Our normal force must also be 98 newtons. Because again, this is the force that is going to be needed to balance out each other and prevent it from either floating off of the ground or sinking into the earth. And since it doesn't mention it doing that in the problem, we know these two things must be canceling each other out. Okay, now let's ask the question of what force do we need of push to get it moving? How hard do we have to push it before it'll start moving? So to do that, we're going to have to see what is the maximum of static friction So that'll be our coefficient of static friction times our normal force. Our normal force is 98. 98 times 0.4. I get 39.2 newtons. So what this means, what this value right here has told me, is that until we pass 39.2 newtons, the object is not going to move. The object will not be moving at all. 39.2 is how much resistance the ground will give if you keep trying to just push it flat against it. So in question A, if the push is 15 newtons, and comparing that to this number right here, there will be no motion. And that's because static friction will stop it. Static friction is strong enough to stop a 15 Newton push. Well, what about B? Well, our information is the same. It's still got the same gravitational force, the same normal force. It's still got the same static force. It's 38 enough. 38 newtons. No motion. Static friction will stop it. Only in scenario C, where we have 40 newtons of force, do we actually have enough to overcome our static friction. So we'll actually need to come up with our kinetic friction. We'll need to be using our kinetic friction. So sum of the forces in the y direction equals 0 equals Fn plus Fg equals, in this case, they're both 98. 98 minus 98. -98. So we know all that information. So now we know the sum of the forces in the x direction is going to equal the force of our push plus the force of friction. But this time it's kinetic friction. Force of our friction is going to be equal the coefficient of kinetic friction times the normal force. Normal force is 98. Kinetic friction coefficient this time is 0.3. 98 times 0.3. I get 29.4. So our push is going in what we'll consider the positive direction. So that's 40 newtons. Minus our coefficient of kinetic friction, which is 29.4 newtons. So I got a 10.6 Newton force. Now, because there is a net force, it asks, describe what happens. So it will be pushed forward. But we also know from our Newton's second law that sum of the forces is equal to the mass times the acceleration. If we know 10.6 is the sum of the forces, we know our mass is 10 kilograms. We can solve our acceleration. And we will have an acceleration that it's going to be moved at. So not only will it be pushed forward, it will be pushed forward at, sorry, this is second squared, at 1.06 meters per second squared. So if you keep pushing with that force, it's actually going to get faster and faster. If you want to just specifically overcome it and keep pushing it at a constant rate, you would just need to fall back, and once you get it moving, you'd need to use this 29.4 newtons. If you keep pushing it at this 40 newtons, you're actually going to be increasing the speed of the box, assuming you're keeping pace with it. Okay. Sorry if that was a little bit confusing and jumbled there at the beginning. Again, I am just trying to get all these done. We got home a couple days ago with my wife, and she's still suffering from some pain meds and some discomfort from it. So it's been some stressful nights. But if you have any questions, please don't hesitate to ask. I'd be happy to try to explain them in more detail. If there's anything I can do, please just let me know. In the meantime, this is Mr. Diamond signing off. I hope you guys have a good rest of your day, and I hope to see or hear from you soon.